All right, so let's look at 7.4, which is all about trig substitutions. So trig substitutions help us to deal with integrals that contain things like, that contain expressions of the form, a squared minus x squared, usually under square roots, right? So square root of a squared minus x squared, square root of x squared minus a squared, or square root of x squared plus a squared. Right? And obviously with addition you can do the addition in any order, so this takes care of both orders. The idea is that we want to let x be something that'll cancel out the square root, and since we have so many nice Pythagorean identities with trigonometric functions, oftentimes we can rewrite expressions like this. If we let x be some trig function, then we can rewrite the expression and then take the square root, and that'll get rid of the square root. In particular, once again, your book has an excellent table, table 7.4.1. This is on page 433, and it tells you exactly what to do. So if you have an expression of this form in your integrand, a squared minus x squared, then a good substitution to try would be x equals a times sine theta, right? A times sine theta. If you've got an a squared plus x squared, then you let x be a tangent theta. And then if you've got an x squared minus a squared, you let x be a secant theta. And that's basically the idea. So what I want to do is just walk you through a whole bunch of examples. So let's do it. Okay. So let's do the integral of dx over x squared times the square root of 4 minus x squared. Now, I'm going to do this using a trig substitution. Are there other ways that we could evaluate this? Potentially. I don't know. I haven't given it a ton of thought, but maybe. If this were just an x to the first power out here, and we just had x times the square root of 4 minus x squared, well, that would be a secant inverse type of situation, right? But because it's an x squared, that doesn't quite work. So what we're going to do instead is we're going to do a trig substitution. And this, this integral has the form a squared minus x squared. This is a 2 squared minus x squared thing. And so the substitution for that is a equals sine theta, right? I'm not going to jump back and forth. It's x equals a sine theta, right? Where a is 2 in this case. So I'm just going to cut to the chase and say, all right, let's do it. Let's let x be 2 sine theta, right? And then dx is going to be, derivative of sine is cosine, right? So 2 cosine theta d theta. So we're going to replace this dx with 2 cosine theta d theta. And we're going to replace all of our x's with 2 sine theta. So we end up with this. dx is 2 cosine theta d theta. X squared is going to be 4 sine squared theta, right? And then this thing is going to be square root of 4 minus 2 cosine theta, or sorry, 2 sine theta squared. So 4 minus 4 sine squared theta. Okay. And now you just have to do a bunch of algebra, trig, right? So for example, here I can factor out a 4 and then take it out of the square root. Square root of 4 is 2. So I can take a 2 out here. Now that 2 will cancel that 2 up there. And this 4 I can take out as a 1/4. So I'm going to get a 1/4 times the integral of cosine theta d theta over sine squared theta times the integral, or times the square root of 1 minus sine squared theta. All right. Well, 1 minus sine squared theta is just cosine squared theta. And the integral of cosine squared, the square root of cosine squared is just cosine, right? And then that cosine will cancel with that cosine. So this is really just 1/4 times the integral of d theta over sine squared theta. And that looks a lot better than what we started with, right? So 1 over sine squared is cosecant squared, right? So this would be 1/4 times cosecant squared theta d theta. And let's see, derivative of tangent is secant squared, so the derivative of cotangent should be negative cosecant squared. So if I put a negative here and a negative there, then this thing is just going to be cotangent theta, right? So this is negative 1/4 cotangent theta plus c. I think. See, this is where it's nice to have to be lecturing in front of a group of students, because then you can let me know if I've gone wrong somewhere. But no, I think that's correct. Negative 1/4 cotangent theta plus c. Okay, now we've got to get this back in terms of x. We let x be 2 sine theta. So here's what I'm going to do. I'm going to draw a little triangle, right? If x is 2 sine theta, then that means that sine theta is x over 2. So if that's theta, sine theta is opposite over hypotenuse. And then I can solve for the adjacent side, right? I can say, well, x squared plus this squared equals 4, right? So whatever this thing is, I should have called, well, maybe if I had drawn the triangle differently, but anyway, x squared plus, well, we'll call it y squared, I suppose. X squared plus y squared equals 4. So y is going to be the square root of 4 minus x squared, right? So this is the square root of 4 minus x squared right there. And then that helps me figure out what cotangent theta is, because cotangent is going to be adjacent over opposite. So it's going to be root 4 minus x squared over x. Okay, so my integral dx over x squared times the square root of 4 minus x squared is negative 1/4 cotangent theta. So that would be times root 4 minus x squared over x plus c. I guess we could make that a little cleaner. We could call it negative square root of 4 minus x squared over 4x plus c. That's maybe a little nicer. But that's that. Okay, so that's the idea behind trig substitutions. That's how trig substitutions work. Let's look at another one. Let's do the integral of the square root of x squared minus 25 over x dx. Okay, now if only the situation was reversed, right? If we had x over square root of x squared minus 25, we could let u be x squared minus 25, and then du would be 2x, which we could fix up, and then we could just have like something, we could have like du over square root of u. Unfortunately, it's the other way around. So what do we do about that? Well, a trig substitution, right? This is the form x squared minus a squared. So that's going to be a secant kind of trig substitution. We're going to let x be a, in this case a is 5, right? So we're going to let x be 5 secant theta. right? And then dx is going to be, derivative of secant is secant tangent, right? So 5 secant theta tangent theta d theta. And so we can replace dx with this nastiness. But we can also replace x with 5 secant theta. So we're going to get x squared would be 25 secant squared theta. So it's going to be the square root of 25 secant squared theta minus 25 over x we replace with 5 secant theta. And then dx we replace with 5 secant theta tangent theta d theta. Okay, so already, you see that those things will cancel at least. Also, you can factor out a 25. Square root of 25 is 5, so you can just completely remove that from the integral. You'll have secant squared minus 1. Well, secant squared minus 1 is the same as tangent squared. So this is 5 times the square root of tangent squared theta times tangent theta d theta. Okay, so that's not scary at all. So square root of tangent. Hold on a sec. Yeah, square root of tangent squared is just tangent. I mean, technically it's absolute value of tangent, right? But let's think about that. Maybe I should have been more careful on the previous one too, but we'll leave that for later. I mean, square root of tangent squared would be absolute value of tangent. If tangent's negative, then we'll get a positive times a negative, which would be a negative. If tangent's positive, then we get a positive times a positive, which would be positive. You know what? Okay, so hold on a sec. So this is why it's important that that we pay attention to this, right? So we've got some restrictions here on theta. So we've got this situation. So theta is between 0 and pi over 2. Well, I don't want to waste a bunch of your time. Basically, I'd have to think through like what justifies us being able to just call this tangent theta instead of absolute value of tangent theta, but I have a feeling it has something to do with these kinds of restrictions and stuff. I do know that it works. I would just have to think through, why we can be 100% confident that it does. But anyway, let me just finish the example. So square root of tangent squared is going to be technically absolute value of tangent theta, but we'll just call it tangent theta. And then tangent theta times tangent theta is tangent squared theta. So we're going to have 5 times the integral of tangent squared theta d theta. Tangent squared, we don't have any trig functions. We don't have any trig functions whose derivatives are tangent squared, but I do know I can rewrite this as secant squared minus 1, and I know that integral of secant squared should just be tangent, and then 1 should just be theta. So, okay, so I'm going to call this 5 times the integral of secant squared theta minus 1, and so that's going to be 5 times integral of secant squared is tangent. Integral of 1 is just theta. Okay. But now we have to back substitute and get this in terms of x again. So again, if x is 5 secant theta, then that means secant theta is x over 5. And so if I draw a little triangle, I guess that's what it is. It's like theta is always going to be acute, so that tangent, so that all the trig functions of theta are going to be positive anyway. But anyway, theta is, so secant theta is x over 5. Secant is hypotenuse over adjacent, right? So hypotenuse over adjacent. So I can say this side that's missing, I can say 5 squared plus y squared equals x squared. So then y is going to be square root of x squared minus 25. Okay, so square root x squared minus 25. Okay, so then tangent theta is going to be square root of x squared minus 25 over 5. Okay, so my integral, square root of x squared minus 25 over x dx, is 5 times tangent theta, which is root x squared minus 25 over 5, minus theta. Theta would just be, I guess, secant inverse of x over 5. Right? So secant inverse, right, theta would be secant inverse of x over 5. And there's our answer. We could distribute the 5, I suppose. Oh, can't forget our constant of integration, right? So we could distribute the 5 and call this like square root of x squared minus 25 minus 5 secant inverse of x over 5 plus c. Okay, but that's that one. Okay, let's do another one. This time let's put some limits of integration on there so that we know how to deal with those. So let's do the integral from 0 to 1 of the square root of 1 plus x squared dx. Well, this is pretty easy. I'm pretty sure we've integrated this one before using like integration by parts or something, right? But let's do this using trig substitution. So in this case, I've got an a squared plus x squared. That's a tangent format, right? So I'm gonna let x be a tangent theta. A in this case is just 1. So I'm going to say let x be tangent theta, right? Then dx would be secant squared theta d theta. Okay, and I can make all of my replacements, right? So I can say, okay, so let's talk about how to deal with these limits of integration. So one thing that we could do is we could convert them to from x limits to theta limits. So we could plug in 0, say, and then say, well, when does tangent theta equal 0? Tangent theta equals 0 when theta equals 0. And then we could say, we could let x be 1 and say, well, when does tangent theta equal 1? It equals 1 when theta equals pi over 4, right? And so we go from 0 to pi over 4. So that's one way that you could handle it, right? Just change the limits of integration from x limits to theta limits. Another thing you could do, though, would be to just ignore the limits of integration for now until you've back substituted for x, and then plug the limits of integration in at that point, right? So you could do it that way too. It's up to you, whichever method you prefer. Maybe I'll show you, oh, I don't know, maybe I'll show you both ways, but I'll show you the second way first. So let's just ignore the limits of integration for now and say, all right, integral of square root of 1 plus x squared dx is going to be, if I let x be tangent theta, it's going to be square root of 1 plus tangent squared theta. And instead of dx, I'm going to have times secant squared theta d theta. That's going to be the integral of the square 1 plus tangent theta is secant squared. Square root of secant squared is secant. And secant times secant squared is secant cubed. So this is just secant cubed theta d theta. Okay? And then from there, you can use that formula from the previous section. So let me pull it out. Actually, I don't need to remove it from the binder because it's right here, the secant cubed one. Right? Just use this formula from the previous section. This is from my 7.3 notes, right? So use this formula. All right, so it's 1/2 secant theta tangent theta plus 1/2 ln of secant theta plus tangent theta, right? Holy schmoly, that's a long answer, right? And we're still not done because if we want to get it in terms of x, then we have some more work to do, right? So if tangent theta equals x, so we'll say x equals tangent theta, implies this kind of a triangle, right? So theta, and tangent theta is opposite over adjacent. X squared plus 1 squared equals hypotenuse squared. So the hypotenuse is going to be the square root of x squared plus 1, right? And so then we can move forward from here and say, all right, so this is 1/2 secant theta. Secant theta is hypotenuse over adjacent. So that's square root of x squared plus 1 times tangent theta is just x, right? Plus 1/2 times the natural log of the absolute value of secant theta plus tangent theta. Okay, so there it is in all of its glory, right? Of course, we can make that look a little nicer. We could call it like x over 2 times the square root of x squared plus 1 plus 1/2 times the natural log of the absolute value of square root of x squared plus 1 plus x. Oh, I don't need the constant of integration because I did actually, because I got rid of the limits, right? Anyway, so if I wanted to do the limits of integration now, well, then I could just plug them in. I could say, oh, okay, so this is x over 2 times the integral of x squared plus 1 plus 1/2 times the natural log, the absolute value of x squared, square root of x squared plus 1 plus x, evaluated from 0 to 1. I bet a lot of things kind of cancel, right? If you plug in 1, well, you get square root of 2, so you get root 2 over 2, and then here you would get another root 2 plus 1. Oh, so maybe it's not so nice. When you plug in 0, I wonder, this is 0. This would be 1 plus 0, which is 1 ln 1 is 0. Oh, so when you plug in 0, a bunch of things cancel off. When you plug in 1, you just get like root 2 over 2, right? Plus 1/2 times, this would be root 2 plus 1. So 1/2 times ln of root 2 plus 1. I don't know why I switched the order. But anyway, so you get something along those lines, right? So that's kind of nasty. But anyway, that's that. As I said, from here, when you do the substitutions, you could just change the limits, right? So when x is 0, tangent theta is 0. When x is 1, when x is 1, When x is 0, theta is 0. When x is 1, theta would have to be pi over 4, right? So you could do it this way. And then after, a lot of toil, right, you get to this step here. And at this step, you could just plug in 0 and pi over 4 everywhere. I'm not sure it's that much easier. You know what I mean? If it's easier at all. So, but it does help you avoid having to like do the back substitution part, right? So you get here, and then you can just plug in pi over 4, and then plug in 0, right? So up to you how you want to deal with those. Let me show you another example. Ooh, this is a nasty one. Let's do x over 16x squared plus 16x plus 5 dx. So this one doesn't even have any square roots. I'm kind of curious if we're even going to end up doing a trig substitution. I kind of think that we won't, but maybe we will. I think the main reason I wanted to give you this example is to show you that completing the square is sometimes a useful thing to do. And so let's do it. Man, but completing the square on this thing, that's going to be so nasty. Oh, goodness. Completing the square. That's horrible. Okay. Well, let me just do some scratch work to complete the square. So I can factor out a 16 and get x squared plus x. And then the 5 maybe I'll leave out here because I want to fill this in with whatever's needed to complete the square. So to complete the square, I do half b squared, right? So half of b is 1/2. 1/2 squared is 1/4. So I really need to add 1/4. But I can't add 1/4 without balancing it out over here, right? And by the way, I didn't really add 1/4, did I? I added 16 times 1/4, which is really 4. So I really added a 4. In order to balance that, I need to subtract a 4. Okay, so now I haven't changed this expression. Like, if you simplify this, you'll get right back here, right? Just to prove it. It's like you've got 16x squared plus 16x plus 4 plus 5 is 9. Then minus 4 is 5 again, right? But the nice thing about this is that now I can factor this as a perfect square, right? So I've got 16 times x plus 1/2 squared, and then 5 minus 4 is 1. So that's that situation. Although, gosh, I'm not really sure that's what I want to do now that I'm looking at it, because I was hoping to be able to take this 16 out and make it a 1/16, but the problem is with the way that I've done this. So here, let me do it slightly differently so that I can do that. So let me try again. Let's do 16 times x squared plus x plus 5/16. And then I'll do 16 times x squared. And this needs to be a 1/4, right? So x squared plus x plus 1/4. 5/16 is 4/16 plus 1/16. So I'll say plus 1/16 like that. And now I can write this as 16 times x plus 1/2 squared plus 1/16. Oh, I suppose, oh my goodness, that's the same thing as this, just with the 16 factored out. Why? You know what, it's too late for me to be recording these lectures. That's the problem, that's really the problem. But anyway, okay, that's fine, that's fine. So I'll take out the 1/16. Okay, so I've got 1/16 times the square root of x over, you can hear my dog snoring, 1/16 times x over, this is going to be x plus 1/2 squared plus 1/16 dx. You know, maybe I don't want to factor. It's just making things complicated, isn't it? You know what? Here's what I'll do. I'm going to, so forget that. I'm actually, I'm going to leave it this way. Okay. Bear with me, guys. So I've got 16 times x plus 1/2 squared plus 1 dx. And in fact, I can put that 16 in there. 16 is 4 squared, right? So really I'm going to call this x dx over 4x plus 2 squared plus 1. Okay. Yes. Okay. That'll work great. Okay, so now let me show you what we can do with this. So we let u be 4x plus 2. And then du is going to be 4 dx. Okay. Now also, if u is 4x plus 2, because notice, like I've got du is 4 dx, but here I've got an x that I still have to deal with. So I can solve for x here. I can say x is going to be u minus 2 over 4. So making all of those replacements, man, this is complicated. Making all those replacements, x is u minus 2 over 4. Dx is going to be du over 4, I guess. You can kind of think of it like that. And then this is going to be all over u squared plus 1. Oh, goodness gracious. 4 times 4 is 16. It's a denominator there. I'm going to go ahead and pull it out. So, see, this is, it's like the 1/16 ends up out here. Somehow, it's going to end up out there. But we've got u minus 2 du over u squared plus 1. Now I'm going to split the integral. This is 1/16 times the integral of u over u squared plus 1 du minus the integral of 2 over u squared plus 1 du. Okay, and now I'm almost done. I know it doesn't look like it, but I think I can get there in one more line. So I've got 1/16. Okay, so notice that if I do another substitution here, like if I let w be u squared plus 1, then dw would be 2u du, right? So the derivative of this is sitting up top here. In fact, I can make it a 2u if I put a 1/2 right there. Okay, so the derivative of this is sitting down here. So this is just the natural log, right? This is just the natural, right? If I did the substitution, it would be dw over w, right? And so that's just going to be ln of w. Well, w was u squared plus 1. So this is times 1/2 times the natural log of w, u squared plus 1. Now, what about this thing? Well, I can take the 2 out and just make this a 1. 1 over u squared plus 1, or integral of 1 over u squared plus 1 is just tangent inverse of u. So this is minus 2 tangent inverse of u. Okay. And then I'm going to distribute that 1/16. So I'm going to get 1 over 32 ln. U squared plus 1 is always positive, so I can drop the absolute values. Minus 2 tangent inverse of u. Then I can back substitute, right? So u was 4x plus 2. So I've run out of space on my paper, but you get the idea now, right? So what's really interesting about these kinds of problems is that you end up with two things that look very similar, but this one's a natural log and this is a tangent inverse. Anyway, we didn't do any trig substitutions here, so there's really nothing new here other than this whole like completing the square business. The completing the square is a technique that'll come in handy, and it does come in handy when you are doing trig substitutions. So let me show you that. Let me put this concept of like doing completing the square, let me put that together with some trig subs. Okay. Okay. So we've got this monstrosity, dx over square root of 2x minus x squared. Okay, so first thing I'm going to do, I'm just going to do some scratch work, right? So 2x minus x squared is really negative x squared plus 2x. I can factor out the negative and get an x squared minus 2x. And I can complete the square by adding a 1. Now, of course, if I've added 1 in here, I've really subtracted a 1. And so to offset it so that this equality still holds, since I've subtracted 1, I have to add a 1. And then I can call this negative x minus 1 squared plus 1. Okay, so I've completed the square. And I can take 2x minus x squared and replace it with this. In fact, let me go one step further and call this 1 minus x minus 1 squared. So I can replace the 2x minus x squared and replace it with a 1 minus x minus 1 squared. Okay? Okay, now this still isn't quite in a format where I can do a trig substitution on it because I just need a variable in here, not like a variable and a constant. But if I do a u substitution first, let u be x minus 1, then I can do a trig substitution later, right? So I'm going to say let u be x minus 1, right? Then du is going to be just dx. And I get du over square root of 1 minus u squared, right? So there it is, right? There it is. Oh, and in fact, I don't even need a trig substitution here. I should have done it the other way around, like x squared minus 2x, because then you'd get to this step and it would be u squared minus 1. And you'd have to do a trig sub. Here you don't have to do a trig sub because this is just sine inverse, right? So this was easier than I intended. This is just sine inverse of u plus c. And you can back substitute now and call this sine inverse of x minus 1. So that didn't quite show you what I intended. Because because I intended to do like a completing the square. Hopefully the next, or I did a completing the square, but I intended to do a trig substitution in conjunction with completing the square and a u substitution. This was supposed to be like my kitchen sink example. But let's look at the next one. I have one more example, and maybe this one will be more like the example that I was intending to show. We'll see. Let's do e to the x over square root of, sorry, going back here, hopefully the idea is clear that like if at this point you had ended up with something that you still couldn't integrate, but you had this kind of format where you could do a trig substitution, then you can do a trig substitution at that point, right? To help you along. Anyway, so 1 plus e to the x plus e to the 2x dx. Oh, how nasty. So this is something that I might do a u substitution now. I might let u be e to the x just so that things are a little nicer. So, and I have a feeling this is going to be a long problem, so I don't have any room to spare. I'm going to cram it all in here. So let u be e to the x, then du is e to the x dx. And making the replacements, then I can replace e to the x dx with du. And so this integral is going to become du over square root of 1 plus u squared. Now let's do, that's the same thing as u squared plus u plus 1. So let's complete the square on it, right? So it's going to be du over the square root of, it should actually be u squared plus u, and if I'm completing the square, I would say plus 1/4. Okay, and then I'm going to have, but originally it was 1, so I need to add a 3/4 as well. Okay, but now this stuff I can call u plus 1/2 squared. And the 3/4 can still come along for the ride. Okay, so so now I can do either I can do another substitution. I could say let w be u plus 1/2 or something, which might be nice. Or I think I could just do the trig sub as is. I could say, this is a tangent theta type thing. So I could say, let u plus 1/2 equal tangent theta. Yeah, because then du would be secant theta or secant squared theta. Yeah, and I would be able to make all of the substitutions, I think, as usual. The only thing I'm nervous about is like when I do the back substitutions, then it might get a little tricky. So you know what I'm going to do? I'm going to do another substitution. I'm going to say let w, it'll just make it easier later, let w be u plus 1/2. Then dw is du, and this thing will equal the integral of dw over the square root of w squared plus 3/4. Okay, so now I'm ready to do my trig substitution. So now I can say let w equal, it's supposed to be a tangent theta. A would be square root of 3/4, so that would be root 3 over 2. So I'm going to let w be root 3 over 2 tangent theta. Okay, then dw is root 3 over 2 secant squared theta. And I get, right, so the integral dw is now root 3 over 2, which I'm just going to pull out, root 3 over 2 secant squared theta d theta over the square root of w squared. So that would be 3/4 tangent squared theta plus 3/4. Okay. The 3/4 I can factor out and then take the square root of 3/4. It would be root 3 over 2. And that root 3 over 2 will cancel with that one. How beautiful, right? How beautiful. So this ends up being secant squared theta d theta over square root of tangent squared theta plus 1. Tangent squared theta plus 1 is just secant squared theta. Square root of secant squared theta is just secant theta. And secant squared divided by secant is just secant. Look at how nicely that simplifies. And we've done 3 substitutions for this problem. That was probably unnecessary, but anyway, we are where we are. And we're getting much closer to the end now. Okay, so the integral of secant theta should be ln of secant theta plus tangent theta, right? Absolute value. And now we just have to back substitute. So to back substitute, first of all, if w equals root 3 over 2 tangent theta, then tangent theta is 2 over root 3. Right? So w equals root 3 over 2 tan theta implies that tan theta is 2w over root 3. So tangent theta is opposite over adjacent. We can solve for the hypotenuse. So we say 3 plus 4w squared equals h squared. So h is the square root of 3 plus 4w squared. Okay, so then coming back here, we've got natural log of absolute value of secant theta, which would be hypotenuse over adjacent. So that's root 3 plus 4w squared over root 3. So there's secant theta plus tangent theta. Tangent theta is 2w over root 3 plus c. Now w was u plus 1/2. And u was e to the x. So I'm just going to cut to the chase. This is ln of square root of 3 plus 4 times u plus 1 times e to the x plus 1/2 squared. Over root 3. So I'm just doing all of my back substitutions. Plus 2 times w was u plus 1/2, but u was e to the x. So it's 2 times e to the x plus 1/2 over root 3 plus c. And that's that. Now you might be able to simplify that and make it look a little cleaner. I mean, for one thing, you could put the square root around this whole thing. 3 over 3 is just 1, and you'd have 4/3. In fact, let me do it. The square root of 1 plus 4/3 times e to the x plus 1/2 squared. And here it's not going to get much nicer, I don't think. We could call it 2 over root 3 times e to the x plus 1/2. Maybe if you distributed it, it would look a little nicer, but that's that, right? That's your final answer. So that was like the kitchen sink example, right? We pulled out all the stops there, but that's that. So that's trig substitution, okay? And you can use it in conjunction with all the other techniques that we've learned in this class.